Hello, AP Chemistry. How are we doing today? Mr. Oglesby here. So today we are going to be continuing, or starting actually, our Unit 7, which is going to be over equilibrium. Now for this, we are going to be working with calculators. So you will need to make sure you've got your calculator. Today's set of notes, which is going to be the introduction to equilibrium and the law of mass action, is going to cover the following units. So the reason I want to do this is, and I'm going to try to start doing this, is this will help you prepare by using those practice topic-based quizzes on AP Classroom. So this is going to be over 7.1, 7.2, 7.4, 7.5, and 7.6. Okay? All right. So equilibrium, what is it? Well, equilibrium is the place where basically you've got your products and your reactants, and they remain constant. So what we've found is that reactions tend to be reversible, where we've got this reaction that can go forward or it can go in reverse. And there's a couple of things to kind of keep in mind when we're talking about chemical equilibrium. First off, it's dynamic. Second, any chemical reaction in a closed vessel will reach equilibrium. And third, at equilibrium, the forward reaction rate is going to equal the reverse reaction rate. So why is that? Well, thinking about it, if I've got a forward reaction occurring, it is going to continue to occur until we've got a lot of extra product, right? Now, as a result of having a lot of product, now that reaction can start to begin to reverse to produce some reactants. And so there's going to reach a point where there's an equal in terms of progressing forward and progressing in reverse. And that would be when we reach our equilibrium. Now, there's two ways that we can see this. The first way is looking at concentration. And we're going to be working with our reactants and our products. Okay, so how does this look? Well, if we talk about concentration, at the beginning of a reaction, your reactants should be very, very high, right? And as that reaction progresses, the concentration of our reactants is going to be decreasing. Now, on the flip side, if we talk about products, products are going to start at 0, but as those reactants are turned into products, the concentration of the products is going to increase. Now, the point that we see right here, where they both start to flatten out, that would be what we call our equilibrium. So this would be our equilibrium. Okay, so, and that would be moving basically onward. We would continue to stay at equilibrium as long as that system is closed. And by closed system, I mean there's no outside forces, nothing's being lost to the environment, everything is contained in a vessel and nothing can escape. Okay, so that would be that closed system. The next one we're going to look at is reaction rate. So for reaction rate, we've got the forward reaction rate, and we've also got the reverse reaction rate. So I'm going to signify my rate of forward reaction in black, and my rate of reverse reaction in blue. So let's look at this. So when I start a reaction, okay, the rate of my forward reaction is going to decrease. Okay? And as that reaction progresses, the rate that my products are going to start to go is going to increase. Now we'll hit a point where those lines are going to be met, and that would again be our equilibrium. So when we look at these, basically these graphs are going to be signifying that change in rate. We know that as a reaction progresses, the forward reaction is going to slow down. Why? Because we've got less reactants to work with. The reverse reaction is going to speed up. Why? Because now we've got more products, and in the reverse, remember your products act as that reactant. So as we progress, basically we're going to see that change in the rate based off of our reactants and our products. And the point to where those two meet, that's going to be our equilibrium. Okay? So let's take a look at this in terms of like if I were to draw a particulate diagram. So if I've got reactant A plus reactant B, and that's going to produce product C and product D. How does this look? Well, so I will start my reactant A. I start with 4. And I just made up a number. So I started with 4 of them. My reactant B, I also started with 4. Like that. Okay? So before equilibrium is reached, what we'll see is that I will first off start to create some product. So I'll have 3 of the reactant B and 3 of reactant A. Well, but as a result of that reaction starting, we're going to start to make some products, right? Well, that means that product C and product D will have started to form. And so that would be before we reach equilibrium. Now, as that continues, what we're going to see is that our reactants and our products, we're going to have that point to where they level out. And so for my reactant A, I would end up with 1, 2. Reactant B, 1, 2. My product, I would have 2 of those. And my product D would be 2 of those. And so what we would see is that when we reach that equilibrium, that we've got that progress, that concentration, those concentrations of the products are going to increase, the concentrations of the reactants are going to be decreasing. Now, eventually we're going to reach that equilibrium. Now, here's the question. Do we have to have an equal amount of reactants and products? No. We can have a different concentration of reactants and products. But what we need to recognize is that there's going to reach a point where it kind of levels out. Okay? I tend to like to think of this as if I were to take 2 jars one filled with water, the other has no water in it. And I took 2 different cups and I started dipping the cups out. So I would take one from the left jar and I'd put it into the right jar. And then I would take my cup from the right jar and I'd scoop out as much as I could and dump it into the other side. I would keep doing that. Eventually what would happen is that there would be a point to where those levels would no longer adjust. Why is that? Well, based off of, this cup can only carry a certain amount back over. This cup can only carry a certain amount back to the other side. And so we're going to get a point to where we're basically transporting the same amount over and over and over again. And that would be our equilibrium that we've reached. Okay? So that's kind of a general idea of what's actually going on with equilibrium. We've got this thought that throughout a reaction, a forward-reverse reaction, when we hit that point to where the reactants and the products basically maintain consistency, that would be our equilibrium. Okay? Now, we actually solved this. And we solved this using the law of mass action. And basically what the law of mass action does is it looks at the concentrations of the different things we have, and it uses their coefficients or the number of moles as exponents. Okay? So let's look at the law of mass action here. So if I've got this right here, so J is acting as a coefficient, K, L, and M, everything there is acting as a coefficient. So when we're looking at these, I could say, 1 sodium plus 1 chlorine produces 1 sodium chloride or something like that, right? Or 2, 1, 2 in terms of their balanced equation. And essentially the law of mass action is going to use that balanced equation. So that's going to be one of the very first things that you should be doing is finding your balanced equation. So this is what that actually looks like. So I'm going to be solving for something called Kc. Kc is what we call the equilibrium constant. And it could be represented by Kc or K or Keq. But again, that's just my equilibrium constant. It's the point where your equilibrium maintains that consistency, the point where you will not see that reactant or product ratio change anymore. So we know that the brackets represent concentration. And remember, concentration is going to be molarity, which is moles per liter. Okay. So let's say I've got this reaction. Okay. And let's say I am solving for the Kc of a reaction. I know that Kc equals the concentration of the products over the concentration of the reactants. Sorry, forgot how to draw an S there for a second. So the concentration of the products over the concentration of the reactants. And that's what we see in this right here. So I had Kc equals the concentration of my products, C and D, to their coefficient, divided by the concentration of my reactants. So concentration of A and B to their exponents. And then I would basically plug in my numbers and solve. So let's say I've got, I'm asking you to write the formula for the equilibrium constant of the following reaction. Let's say I've got NH4Cl, and this is a reversible reaction, and it's going to produce NH3 plus HCl. Okay. First thing that I would need to make sure is that my reaction is balanced. In this case, it's balanced for you. Okay. So what do I need to do? Well, I know that I have the Kc, and it's going to equal the concentration of my products, so the concentration of NH3, to its coefficient. Okay, so looking here, there's only a 1 there, so we're just going to leave it at NH3. And then I have the concentration of HCl. So those would be my products divided by the concentration of my reactants. So the concentration of NH4Cl. Okay, and so that would be the Kc, that would be my equilibrium constant. That would be how I would solve for it with this given equation. Okay. Now, here's something to note. If I'm talking about the concentrations of a pure solid or pure liquid, we're not going to include them in equilibrium expressions. And the reason is because they maintain consistency. They're going to stay constant. And so when we look at a solid or a liquid, we just completely ignore those in terms of our Kc equation. Okay. So here's an example. It says I've got CaCO3, and that produced CaO and CO2. So I need to solve for my equilibrium constant. So Kc equals, well, it's products over reactants, right? So I would do the concentration of, my products. But CaO is a solid, so we don't worry about it. So we can ignore CaO, and then I've got CO2 divided by the concentration of my reactants. Again, that's a solid. So my Kc in this case is just going to equal CO2. Okay? Now, here's the deal. K is going to change with our temperature. So one of the things that we've noticed is that our equilibrium constant changes with that temperature. Not concentration or pressure. If I change my concentration, why would that not affect my K? Why would that not affect that equilibrium constant, that point at which we reach equilibrium? Well, remember that as I add more reactants, what's going to happen? Well, those reactants are going to turn into products, right? And then that reverse reaction is going to continue. And we'll see this equilibrium actually doesn't move because those reactants are changing into products. Okay, and so we see this equilibrium constant. It stays the same because there's nothing that's going to affect that. Now, why does temperature cause a change? Well, temperature causes a change because temperature, think in terms of solubility. If I take, table salt, and I add some table salt into water. I can add enough salt to where it will not dissolve anymore, right? Yes. So I can add enough table salt to where it will not dissolve anymore. So then what happens when I heat that up? Could I dissolve more table salt? Yes, I could. And so what we see is that increasing my temperature causes that equilibrium constant to change, right? So increasing or decreasing the temperature can end up causing that change in the equilibrium constant, okay? Now, if I've got 4NH3 plus 7O2 produces, in a reversible reaction, 4NO2 plus 6H2O, which is a gas, then what do we get for our Kc? Okay, well, if we know equilibrium concentrations, we can actually calculate our equilibrium constant, our Kc. So what they want us to do is they want us to actually write the expression for the equilibrium constant, which remember could be Keq or Kc or just K. So let's take a look at this. So I've got 4NH3, 7O2, 4NO2, and 6H2O. Okay? Well, I know for my Kc, what I do is products over reactants. I do my concentration of my products over the concentration of my reactants. So my products were NO2 and H2O. Those would be my products. Now, both of those are gases, so we are going to use them both. Okay? So I've got NO2. It's going to be to the fourth power. Why to the fourth power? Well, it's to the fourth power because I've got 4 as my coefficient. Okay? H2O is going to be to the sixth power. Again, because that's the coefficient. So I do the concentration of NO2 to the fourth power times the concentration of H2O to the sixth power. And then I'm going to divide that by the concentration of NH3 to the fourth power and the concentration of O2 to the seventh power. And so then if I had those concentrations, I could actually plug in my numbers and actually solve this problem. So what I want y'all to do is I actually want y'all to take a second and to pause your video and try to find the equilibrium constant equation that you would use for these two formulas. So pause your video, solve these two, and then we're going to go over them. All right, so this is what you should have ended up with for your two KEQs or KCs or Ks. So for the first equation, I found that I had KEQ equals the concentration of H2O, which is again my product, to the second power because of its coefficient here, divided by the concentration of H2, which is a reactant, to its coefficient, and then times the concentration of O2 times its, or to the power of its coefficient, which is 1, so we don't worry about it. Okay. On the second one, I have NOBr to the second power, so products, concentration of products. And then I have NO to the second power and Br2 to the first power. Okay. Now, you've got a general idea of how to do your KEQ equations. So what happens if they actually give us the concentrations? Well, let's take a look at this. So it says write the expression for the equilibrium constant for the following reaction. Using the expression, calculate the value for KEQ based on the equilibrium concentrations given. So KEQ is basically solving for our point at which we've reached equilibrium. Okay. What I would do is I would start with my KEQ. I personally like to write out my formula first. So is the concentration of my products, NH3 to the second power, divided by the concentration of my reactants, N2 and H2 to the third power. Okay? Then what you would do is you would actually plug in your equilibrium concentrations that you're given. So my KEQ for NH3, I found that I have 0.0100 molarity, and it is going to be to the second power. I'm going to divide that by the concentration of N2, which was 0.0200, and the concentration of H2, 0.0200 to the second power. So then all I would do was plug those numbers into my calculator, and I would find my KEQ is going to equal 12.5. And that would be my answer. So that's all you do for equilibrium. You're just basically going to plug in your numbers and solve, okay? Or for the equilibrium constant. So now what I want y'all to do is I want y'all to solve this next problem. So first off, start with your equilibrium expression so that KEQ equals, like in this case, NH3 to the second power divided by into the concentration of N2 times the concentration of H2 to the third power. So I first want y'all to write that equilibrium expression. And then afterwards, I want y'all to actually solve for your KEQ. Okay, so pause your video, solve for that KEQ. All right, so let's take a look at this. So I've got KEQ equals the concentration of KCl to the second power times the concentration of O2 to the third divided by the concentration of KClO3 to the second power. I plugged in my numbers. I got 0.00250 to the second, 0.0500 to the third, and all of that is over 2.00 to the second. Plug that into my calculator, and I found that my KEQ is going to equal 1.95 times 10 to the negative 10. Okay? So very, very simple in terms of how we would solve that. Now, this is basically going to be solving for the forward reaction. So we're looking at that forward reaction. We're saying, okay, well, what actually occurred? Okay? Now, for the reverse reaction, so let's say I had this. So these two were my products, so I flipped it. These were my reactants. Okay? We've got our coefficients. So what's actually going to occur? Well, now our products are the reactants, and now our reactants are the products. So you're like, okay, well, now you would just solve it the same way you did, but again, it's the reverse reaction, right? So you know that the reactants became the products, so those would go on top, and the products became the reactants, so those would go on the bottom, right? Well, there's a simpler way to do it. If you've already solved for the Kc, okay, for the forward reaction, you can solve for the reverse reaction Kc by just doing the inverse of it. So 1 over your Kc, and that will actually give you your Kc of your reverse reaction. Okay, so it is very, very simple to actually reverse that and solve for the reverse reaction just by doing that inverse of that Kc. Okay, now let's say, here's another way that we could do this. Let's say the original reaction is multiplied by a factor. So instead of saying I had 2 Na plus 1 Cl produced 2 NaCl, I said I have 4 Na plus 2 Cl produces Cl2 produces 4 NaCl. Okay, well, in that case, I multiplied by a factor of 2, right? Well, the nice thing about that is basically what I can do is plug that in as a factor that I'm working with, okay? And basically, I could solve for my Kc using that factor as a part of that exponent. Now, okay, well, how do I do that? How do I make that simpler? Well, all I would do is I would take my Kc and multiply it by put it to the exponent of whatever the factor is. So if I used a factor of 2, then I would go my Kc to the factor of 2. If I had a factor of 1/2, then I would go Kc to the 1/2 power. And so when I'm solving for these, it is very, very simple just to use that as a kind of a shortcut for solving these. So let's say if I've got a two-step reaction. Let's say I've got the Kc of 1, the first reaction, and the Kc of 2, the second step, right? As their Kc values, the overall Kc value, so the Kc of the total, is going to equal those two original steps multiplied together. So the Kc of step 1 and times the Kc of step 2. Okay. Now, The unit, if we're talking about K, really does depend on the reaction, and so we typically don't even bother with it, okay? And so you don't tend to put a unit on Kc. So if you look at the previous KEQs or KCs that we've solved, you've noticed that we haven't put a unit. It's because we don't typically use a unit, okay? So let's look at this. It says the following equilibrium concentrations were observed for the Haber process at 127 degrees Celsius. So the Haber process is just taking nitrogen and hydrogen and producing ammonia. And that's a reversible reaction. So looking at this reversible reaction, first off, it asks us to calculate the value for K. Okay, how do I do that? Well, remember that my K is going to equal the concentration of my products, NH3, to their coefficient, divided by the concentration of my reactants. So N2 and H2 to the third power. So if I'm solving for my K, I basically plug in my concentrations. So what I found was that my K equals the concentration of NH3, which was 3.1 times 10 to the negative 2 to the second power, divided by the concentration of N2, which was 8.5 times 10 to the negative 1, times the concentration of H2, which was 3.1 times 10 to the negative 3 to the third power. So then I would plug that into my calculator, and I would find that my K equals 38,000. Okay, it's a really big number. Now, the next thing it asks us to do is to calculate the value of the equilibrium constant at 127 for the following reaction. Well, what happened? Well, all we did was we reversed the reaction, right? And so when we reverse the reaction, all we would need to do, we know that if I've got my Kc of my reverse reaction, that equals 1 over my Kc. So I could then just plug in my numbers for that. So Kc of my reverse equals 1 over 38,000. And I would find that my Kc of my reverse reaction would equal 2.6 times 10 to the negative 5. Okay, again, just a very, very simple way. You could technically plug everything into this, right? But reversed. So you'd have your reactants on the top and your products on the bottom. But that's a lot more work. If you've already solved for your Kc, there's no reason not to just use this inverse equation. Okay? All right, now let's look at this next one. So this next one says, calculate the value for the equilibrium constant at 127 degrees Celsius for the reaction given by the equation. And it looks like it skipped to the other page. 1/2 N2 plus 3/2 H2 in a reversible reaction produces NH3. Well, what happened here? Well, in the case of this reaction, what did we do? We have a factor of 1/2. And so since we've got a factor of 1/2, I know that if I've got my Kc, it can equal, the Kc of that integer, right? Of that factor, it's going to go to the nth power, so whatever my factor is. So my Kc was 38,000, and my factor was to the 1/2 power. So I would just do my Kc equals 38,000 to the nth power, which would tell me that my Kc equals 190. And that would be my answer for that. Okay, so let's take a look at what all these numbers mean. Well, essentially, we've got an equilibrium position. So an equilibrium position is going to be my set of equilibrium concentrations. So in the case of this reaction, my equilibrium positions are going to be for NH3, 3.1 times 10 to the negative 2. N2 would be 8.5 times 10 to the negative 1. And H2 would be 3.1 times 10 to the negative 3. Okay, so that's basically the position that we're talking about in terms of equilibrium. Okay, now the equilibrium position does depend on our initial concentrations, but the Kc is not going to depend on that. So basically, where we're talking about in terms of that does depend on the concentrations that we start with. So let's actually look at pressure. So we've already talked about equilibrium constants, and that's having to do with concentration. But what about pressure? Well, pressure can also be used in terms of those equilibrium expressions. The equilibrium constant for pressure is Kp. Kc would be your equilibrium for the concentration. Kp would be the equilibrium for the pressure. So if we're using the same mass action equation above, we can solve for our Kp expression. So again, same thing, but this time we're actually using pressure, okay? So the Kp is going to equal the pressure of C to the whatever exponent it is, times the pressure of D to whatever exponent it is, so L and M, and then we do our reactants on the bottom, so the pressure of A to the J and the pressure of B to the K, J and K. So one thing I will first off remind y'all of is that if we're talking about pressure, we're not talking about concentration, right? And so we will not use those brackets in terms of pressure, because those brackets, remember, those represent concentration. Now, P is going to be whatever the partial pressure is at equilibrium, okay? And so when we're looking at each individual substance, then each individual substance provides a pressure to the actual system, right? And so P is going to represent the pressures for each of those substances. Now, this does need to be in atmospheres, so you need to make sure that you know how to convert. If needed, you need to make sure you know how to convert from like kPa or mmHg, okay? So again, Kc involves concentration, Kp involves pressure. But again, essentially, you're going to solve them in the same way. Kp is going to be solved using our equilibrium expression, just like we did with our Kc. Okay? Now, are they the same thing? No, they're not. One has to do with concentration, one has to do with pressure. But we do have a formula to allow us to actually convert from one to the other. Okay? And so we can actually convert them using this relationship right here. So my Kp equals the Kc times R, which is our gas constant, right? Times temperature in Kelvin, it does need to be in Kelvin, to the number of moles, the change in that number of moles, okay? So what does that mean? So what we would do is we'd find the number of moles of our products minus the number of moles of the reactants. So let me give you an example of how to solve for the number of moles. So if I have 2H2 plus O2, and that produces 2H2O, then for my reactants, my number of moles is 2 here and 1 here. So that's a total of 3 moles. And my products is 2 there. So if I were finding my total, then I would do products minus reactants. So my products would be 2 minus my reactants, which would be 3. So 2 minus 3 would give me -1 in terms of that. Okay? Okay. Now, here's something to note. This is actually a shortcut that you could potentially use. Your Kc can equal your Kp if the number of moles of the gaseous product equal the number of moles of the gaseous reactant. Okay? So your Kc can equal your Kp if their number of moles are equal. So the products and the reactants, the number of moles are equal. Okay? All right, so what does this KEQ actually mean? Well, what it tells me is that I can have either reactant or product favored reactions. And so what we'll see is that reactions will continue until we reach equilibrium, and they'll continue after that point. But once we reach equilibrium, that rate that concentration, those pressures are basically going to be consistent after that point. Okay? So if I solve for K and I find that K is greater than 1, what that tells me is that it is products favored. Okay? So it's products favored. And what that means is that the reaction is going to shift to the right to start to make some more products. Okay? Now, let's say my K is less than 1. What that tells me is that it is reactants favored. So we've got a lot of product now. So now we're going to become reactant favored and start to produce some more reactants. Okay? And so it's basically telling us how is this reaction going to shift to where it will finally reach equilibrium. The next thing in terms of KEQ, what does it mean? In terms of understanding KEQ, one thing to keep in mind is that the size of K does not necessarily directly relate to the time that it will take for it to reach equilibrium. And this was actually covered in kinetics when we talked about kinetics in Unit 5. Just because we've got a lot of reactants or products, that doesn't necessarily mean that the reaction is going to occur very, very quickly. Okay, and so that's all that is saying, is that just keep in mind that just because I've got a very big or very small K, that doesn't mean it's going to affect how fast my reaction occurs. Okay. Next, K values can not always be directly compared because their stoichiometry is going to differ. So basically, each reaction is its own thing. So we can't directly relate two different K values. Okay, so do keep that in mind as well. All right, so that is everything. So the very last thing that I would like for y'all to do is to pause your video and solve this entire next equation. Solve this entire problem. Y'all, this is basically an FRQ that you could see on something like your AP exam, where we talk about, you go through, you solve for K, then you solve for the reverse reaction, the K of the reverse reaction. Then you solve for it based off of your factor, or you're going to solve for the P of K. And so I want y'all to go through and solve all 4 of these, and then we're going to go over it. Okay? All right, y'all. So here is what you should have ended up with. So when you calculated the value of K for this system at 35 degrees Celsius, you should have found your K to equal 1.55 times 10 to the negative 5. When you solve for K when your reaction flipped, basically you would do 1 over your K value, which would give you your Kc of the reverse reaction to equal 64,500. When you calculated for K with that factor being a 2, you would find that your Kc equals 2.40 times 10 to the negative 10. And then last, when you solve for Kp, what you should have found was that it equals 3.92 times 10 to the negative 4. All right, y'all. So that is it for kinetics. I know this was a very long lesson, but thanks for sticking through. As always, let us know if y'all have any questions, but otherwise, y'all have a great rest of the day. Bye, y'all.